what we monitor eye movements. So by fixations, we mean short times when we stabilize our gaze at certain locations. And as you can see, because these fixations come from different people, people are relatively highly consistent in choosing fixation targets. This led to the idea that we can model this process easily, because we can model the process of selecting targets for fixations. So these models predicting locations of fixations are called saliency models, and here you can see sample outputs of one of the models. So colorful regions indicate where, according to the model, people would look given the images. As you can see, this model works really well. So this led to the idea that maybe human brain does something similar. But human brain as well uses image features, because models use just image features, to select where to look. So this is one of the possible explanations. However, it was always a bit controversial, because on the other hand, we can always say, well, maybe our brains care more about the meaning of what we see, about the semantic information, because we see the world around us as a full of meaningfulness. We don't see just edges and colors. We see things, people, and objects. However, here comes the big methodological difficulty, because how do we measure meaning? If we take an image like the ones from the previous slides, how we can tell what's meaningful and what is not in some interesting way. So recently, there has been an idea of how to tackle this problem, how to measure meaning. Recently, one research group proposed so-called meaning maps as a way to quantify distribution of meaning over the image. So, how to construct a meaning map? Let me explain. So, we take the image, here it's indicated by the gray square, and decompose it into a set of circular, partially overlapping patches of two sizes, fine and coarse, and then each patch is separately rated for its meaningfulness. So it's shown to the participant, and participant rates to what extent it's meaningful. And we collect ratings for all patches from a given image. Importantly, each patch is rated by 3 different people, and then they're combined into a smooth distribution, which looks like that. So similar to saliency models. This method is quite novel, and in our work, we decided to put it to the test. So, of course, we cannot escape from a more basic question, the question about the role of meaning in guiding human gaze. So, here we can formulate the first part of predictions. So, if meaning maps in fact measure meaning, and if meaning guides human gaze, then meaning maps should be better predictors of fixations than saliency models, which use just image features. Features which, importantly, might be correlated with meaning, but not necessarily are. So, how to test that? Experimentally, of course. So, at first, we collected eye tracking data for 36 natural scenes. We basically invited observers to eye tracking laboratory where we showed them the images for 7 seconds each, where they had no specific task, they just had to free view them. And we also constructed meaning maps for these images. Given that we needed ratings for over 6,000 patches, we used crowdsourcing platform Amazon Mechanical Turk. So, okay, we have eye tracking data, we have meaning maps, now we need saliency models. So we decided to use three of them. First 2 are GBVS and AWS. So first one is very popular, quite old, and importantly used as a point of comparison with meaning maps before. AWS, on the other hand, is a bit less well known, but performs much better than GBVS. Importantly, both models share one characteristic, that they use relatively simple visual features like orientations, edges, and colors. So they are really simple. And the third model is a deep neural network. This is DeepGaze-2, currently state-of-the-art model. We do not have any better model predicting human fixations than this one. How it works? Well, it's composed of 2 main parts. First of them is a set of fixed features, fixed layers from the VGG feature object recognition network. These layers have a fixed set of parameters, and on the top of them there is a set of additional layers which are trained on human eye tracking data just to predict fixations. So this model uses very complex features to predict fixations. And it does it really, really well. So, to sum up, we have two relatively simple models and one very complex model, namely the LeapGaze-2. Okay, so let me just remind you what we plan to do. So, if meaning maps measure meaning, and if it really guides human gaze, then meaning maps should outperform models. No matter what features they use, meaning maps should be better. Well, let's see if it is the case. So this is the example of results for one scene. On panel A, we have a smooth distribution of human fixations. This is just a set of fixations smoothed with a Gaussian kernel to obtain a smooth distribution. And on panels B, we have meaning maps, and on C and D, AWS and LeapGaze-2. They're quite similar. And if we want to quantify the results, what we can do is to correlate the distributions of obtained from fixations and from a certain model. So the higher the correlation between two distributions, the higher the similarity, and therefore the model predictions are closer to human data. This method is well established. It's one of the many possible methods of comparing models to human data, but it works reasonably well. So let's take a look at the results. So here on y-axis we have correlation of model predictions with human data. Again, the higher the better. And on x-axis we have LeapGaze-2, so this deep neural network model. We have meaning maps, and we have two models using simple features. So we already see the pattern here, because each line indicates predictions for a single scene. But let's take a look at statistics. So going from the GBVS side, and we are mostly interested in meaning maps, they are better than GBVS models, so the simplest one, and this is in line with previous results. They are no different, at least in statistical terms, from AWS, so the model which is a bit more complex but still uses simple features, and most interestingly, LeapGaze-2 outperforms meaning maps. Despite the fact that it's insensitive to meaning. So this result tells us that maybe meaning maps are worth further investigation. Maybe we should look into them further. And this is what we do. In the second part of our studies, we again formulate predictions. This time, if meaning maps measure meaning, and if meaning guides human gaze, then meaning maps should predict changes in distributions of fixations elicited by the manipulations of meaning. So if we take a certain scene, change something in it, people should react to that because meaning is changed, and meaning maps should be sensitive to that as well. So how do we do that? We use openly available Seagram image database. It's a set of images which come in pairs, and in each pair one image is in so-called consistent condition and one is the inconsistent one. So if you haven't spotted the difference yet, let me highlight it. Just one item within the scene is swapped for another. So in the consistent condition, all items are consistent with a scene context. They are items which would be normally found in certain contexts. In the inconsistent condition, one item is swapped for something which you normally wouldn't expect in that context. So we introduce a semantic conflict. This region of scene suddenly becomes much more meaningful. Okay, so how do we analyze the data? So we collected the, again, eye tracking data, LeapGaze-2 predictions and meaning maps data for these images, and if we want to compare predictions, if we want to compare the results from all three, what we do is we quantify how much distribution mass falls within these critical regions. So, and by critical regions, I mean the regions outlined in yellow. So, here is the first result. On y-axis, we have distribution mass falling in a critical region. So, basically, how much distribution falls within this region in consistent and inconsistent conditions. and on x-axis we have conditions. So firstly, human data. As expected, people do look significantly more to the regions which are manipulated. So people are sensitive to manipulations of meaning. However, neither meaning maps nor deep gaze 2 exhibit similar sensitivity. They're completely blind to that. Even meaning maps are scoring slightly lower in the inconsistent condition. So this discrepancy shows us that manipulation of meaning affects human behavior, but not behavior of deep gaze 2 and meaning maps. So to conclude, just for the sake of time, let me just display the take-home message. Yes, people do care about meaning, however, we are still not able to measure it properly. And let me thank Christoph Teufel from Cardiff and Tom and Matthias from Tübingen, authors of Deep Gaze 2 model for collaborations, and I'm happy to take questions.
Thank you very much.